Case 1. So model 2, balancing of rotating masses. So we have different cases here. So we'll learn about the different cases of balancing. So first case is balancing of rotating mass by a single rotating mass in the same plane. Same plane means in the same axis, vertical axis. So as you can see here, so there is a mass m1 on the shaft. Also equally on the opposite, exactly opposite on the side, we have mass m2. So mass m1 we consider as the disturbing mass, and the mass m2 is the, so here mass m1 is the disturbing mass of having a radius r1 from the axis of rotation, and mass m2 is the balancing mass with the radius r2. So considering, so this the disturbing mass, which is on the axis of rotation, rotates at velocity of omega radians per second. So r1 is the radius of rotation of mass m1, or anything but the distance between the axis of rotation of the shaft and the center of gravity of the mass m1. So when the mass m1 rotates, it exerts centrifugal force on the mass m1, which is given by F1 m1 omega square r1, which is given as equation number 1. This force is the centrifugal force which acts radially outwards and produces bending moment on the shaft. In order to counteract this effect of the force F1, the centrifugal force F1, a balancing mass m2 has to be placed in the same plane and exactly of rotation and exactly opposite to that of disturbing mass. So the centrifugal forces due to two masses should be equal and opposite. So here let r2 is the radius of rotation of mass m2, distance between the axis of rotation of the shaft, the center of gravity of the mass m2. So centrifugal force due to mass m2 will be F2 equals to m2 into omega square r2, equation number 2. So if we equate both equations 1 and 2 to balance the system, then we get F1 equals to F2, m1 omega square r1 equals to m2 omega square r2, or m1 r1. So omega, that is angular velocity, is common to both the masses, since it is since both the masses are attached to the same shaft. That's why we can neglect omega on both sides. So we have m1 r1 equals to m2 r2. That's equation number 3. The product m2 r2 can be split, so it can be split in any way. So either we can keep the mass bigger, or the radius shorter, or radius longer and the mass smaller. So this was about the first case of rotation. So simple one. So next we have case 2. So case 2 is nothing but the balancing of single rotating mass by two masses rotating in different planes. So we have single rotating mass, single disturbing mass, which is balanced by two masses which are in different planes. So why we need to use two masses, we'll see later. So here there are two possibilities. So these are the disturbing mass maybe between the two balancing masses. First, in this one more, so we have the disturbing mass may be on the left or right side of the two masses, balancing masses. So in order to balance the single mass by two masses in different planes, which should be parallel to the rotation of mass, so here the net dynamic force on the shaft must be 0. That is, the center of system must lie on the axis of rotation, and this is called the static balance, or the center of mass should be on the axis of rotation. It's called static balance. Means at rest, at rest, the center of gravity Cg should be on the axis of rotation. Second, the net couple due to dynamic forces acting on the shaft must be 0. That is, the algebraic sum of the moment should be 0. So which is nothing but the dynamic balancing. So here, so out of these two, so we'll consider one by one. The first possibility, that is the disturbing mass in between the two balancing masses. So here the figure shows disturbing mass M, as the disturbing mass M is at the center, and the balancing masses are on the either side, that is M1 and M2. So the distance between the two masses are L1 and L2. They're separated by L1 and L2 on the planes M and N. The distance mass is at the plane A, and the overall length of the mass is overall length of the two balancing masses are of length L. So the disturbing mass has mass M with the radius R, and the balancing mass has M1 with the radius R1 and M2 with the radius R2. Okay. Now considering the disturbing mass M lying on plane A is to balance by these two masses M1 and M2. So let R1 R2 are the rotation mass of this plane A, M and N. L1 L2 are the distances between the plane A and M, A and N, and M and N respectively. So the centrifugal force exerted by mass A, mass M or plane A will be F equals to M omega square R. Similarly, equation number 1. Similarly, the centrifugal force exerted by mass 1 on plane M is F1 equals to M1 omega square R1. That is equation number 2. Okay. So now finding the centrifugal force of the other balancing mass, that is M2 on plane N, will be F2 equals to M2 omega square R2. So for static balance, since the disturbing mass M is on one side and the balancing mass M1 M2 are on the other side, so the centrifugal force of the disturbing mass M should be equal to the centrifugal forces of the two balancing masses, that is M1 and M2. That's why the centrifugal force static balance Fc equals to Fc1 plus Fc2. That is, Fc is the centrifugal force of the disturbing mass, Fc1 is the centrifugal force of balancing mass 1, Fc1 is M1, Fc2 is the balancing mass of centrifugal force of the balancing mass M2. Substituting the values, so Fc is M, that is balancing disturbing mass M omega square, and with radius R is equals to Fc1 is of balancing mass 1 M1, so M1 omega square R1. Fc2 is the balancing that is the centrifugal force of the mass 2 and 2 omega square R2. So neglecting the omega because it is common, all three masses are on the same axis, so we can cancel out omega. So we have Mr equals to M1 R1 plus M2 R2. This is equation number 4. Now to determine the magnitude of balancing force in the plane M, or the dynamic force at the bearing O, so we have to take the moments about P, which is a point of intersection, and plane N about the axis of rotation. So the centrifugal force F1 into L should be equal to the centrifugal force F into L2. Taking moments about P, or M1 omega square R1 into L, M omega square R into L2. Therefore M1 R1 L, M R L2 So M1 R1 MR L2 by L. Equation number 5. In order to find the balancing force in plane N, the dynamic force on bearing P of a shaft take moments about O is point of intersection of plane M and its of rotation. So therefore F2 into L is equals to F into L1 M2 omega square R2 into L M omega square into L1. So therefore M2 R2L MRL1 is equal to MR2 R2 MRL1 by L. That's equation 6. So when we balance 5, 6 should be satisfied along the 4. Now the other possibility on the case 2, that is the disturbing mass M lies on the left side here, and the balancing mass M1 and M2 are on the other side. So here M is on the left side here, as you can see on plane A, disturbing mass and M, and balancing mass M1 on plane M, balancing mass M2 on plane N, and the lengths are L1 from the M to plane A to M, and L2 from A to N, and L from M to N, having the radius same radius. So for disturbing mass M having the radius R, for M1 R1, and for M2 R2 we have the radius. So for static balance, F's here, since the mass M1 is on one side, M1 and 2 are on the upper side, so the force, centrifugal force of mass M1 should be equal to the centrifugal force of mass M2, because these two M1 and M2 will be pulled to the upper side and M1 will be pulled to the lower side. So that's why the centrifugal force of M1 should be equal to centrifugal force of the mass M and M2. That's why FC1 equals to FC plus FC2. So yes, elaborating M1 omega square R1, M omega square R plus M2 omega square R2. Neglecting the omega, we have M1 R1 and is equals to M plus MR plus M2 R2. Equation number 1. So this was the static balance. Now for dynamic balance, the unit dynamic force should be 0. Now to find the balancing force in the plane M, or dynamic force bearing O of a shaft. So taking moments about P. So for taking moments about P, then the central force into L, Fc1 into L, should be equal to the central force of the distributing mass into L2, or M1 omega square R1 into L equals to M omega square R into L2. Therefore M1 R1 L MR L2, or M1 R1 MR L2 by L. Question number 2. Similar to find the balancing force in the plane N, taking moments about O, centrifugal force F2 into L about O, Fc into L1, M2 omega square R2 into L, M omega square R into L1. Therefore M2 R2 L into MR L1, or M2 R2 into MR L1 by L. So this is question number 3. So this was about the case 2. So once again, I will just go through. So case 1 is balancing of single mass or rotating mass in the same plane. So here the reduced equation is M1 R1 equals to M2 R2. This is the main equation to balance one mass. Now case 2, as you know, case 2, so there are two cases. So to balance the mass, so this is equation 5. M1 R1 is MR L2 by L should be remembered, and M2 R2 MR L1 by L, equation number 6, should be remembered to balance that there is a resisted mass which is at the center. On the resisted mass which is at the one side, so remember the equation M1 R1 M R L2 by L, M2 R2 MR L1 by L. And you see that this equation 2 and 3 also matches with equation 5 and 6.